This is the Chapter 5 multiple choice solutions. So, number 1, the question is, are B and S mutually exclusive events? So that means, do they, can the events happen at the same time? So a Venn diagram for mutually exclusive would be two circles that don't touch each other. There's no overlap in the circles. So the thing I needed to figure out is, if I started making the Venn diagram, would there be anything other than 0 inside that football, that overlap in the middle? Okay, so I knew there were 78 total. I knew there were 35 in band and 32 in sports. I did not know how much overlap there was, though. So they did say there was 16 who are not in the band or on a sports team. So I knew that 16 would be that number on the outside. Okay, so I knew that this was not. Okay, so then I did 78 minus 16 to get that there's 62 in the or section, in the union of the two circles. So that includes all the parts of the circles, was 62. So then I thought, okay, if there's an overlap, I could go 35 plus 32 and then subtract off the overlap. This is that general addition rule. That would give me my or number. That would give me how much is in the two bubbles together. So I just went forward with that, and I got that x was not 0, x was 5, which means they are not mutually exclusive, which makes A the correct answer. Okay, for number 2, this was pretty simple with just that conditional probability rule. So probability of B given A, 0.25, they gave you that. They gave you probability of B and A. And by the way, probability of A and B is the same as the probability of B and A. And it doesn't matter. This is like a multiplying sort of thing. You can multiply in any order. Okay, so that's 0.08. And so then I just solved it for P of A and got 0.32. Okay, for number 3, okay, they wanted to know chances of your number on your dice being less than 3. So that means a successful event would be 1 or 2. And there are 6 things that could come up total, right? So we're interested in 2 out of 6, or that reduces to 1 out of 3. So that is why we knew it was A. The other issue that came up, knowing that it was A and not D or E, is around probability is always around the long run. That's that law of large numbers. So the long run relative frequency is the key here. In D and E, we're talking about only 3 rolls. That is not the long run. That's the short run. That is not what probability is about. Probability is about averages in the long run. Okay, number 4. I just got to reread these. So we know probability of success is 0.8, and we're creating a simulation to represent that. So we're told to use the digits 0 through 9. So that's 10 digits total. 1 through 9 is 9, plus 0 makes 10 digits total. And we need to assign them so that 80% of the time, or 0.8 is a probability, we get making the basket, and then that leaves 20% missing the basket. Well, if there's 10 digits total, we need 8 of those 10 to be making it, and 2 of the 10 to be missing it. And the one that fit that description was E. 0 to 7 is going to be 8 digits total, because again, 1 to 7 is 7, plus 0 makes 8. And then that leaves 2 digits being a fail and not making a basket. Okay, number 5. There were lots of ways you could have gone through number 5. Oh, that's getting really tiny. Okay, I did it just by adding things up. I knew some of this battle is just working through the wording. They wanted to know what's the probability that they are not from high school B, given that they're not planning on going to college. They did something other than college. So I just had to think through that and think, okay, start with the given. The given is our new denominator. So these are all the ones that are not going to college, those totals. So I added those up. And then the top is within that given. What are the ones that fit our other description of not being high school B? So that's the other green circles. I added those up. You also could have done things around 1 minus. Since it's a lot of complements, you could have found like the probability of being high school B and then subtract it from 1. There are other ways you could have approached this. I just did it by adding. All right. So anyway, so once I added those up, then I got this answer. Okay, so for number 6, we want to know if they're mutually exclusive and independent. So first of all, mutually exclusive means that A and B cannot happen at the same time. So the probability of A and B would be 0 if they're mutually exclusive. And they're not. A and B is 0.375, not 0. So not mutually exclusive. And then separately, to test our independence, I tried out our independence multiplication rule. So if our probabilities are independent, we, this rule should be true. You should just be able to multiply A and B to get the and version. So I tried it out and it worked. So yes, they're independent. So not mutually exclusive. Yes, independent. That was C. Okay, for number 7, the thing I know, like when I first looked at this, my eyes got all fuzzy because I was like, holy cow, that's a lot of notation. But then I started noticing there's a pattern. They're all, the first thing is A and complement of B, and then these are all A and B, and these are all, the same. So really it's the same pattern. So if I just tried out one of them, we'll see if it works or doesn't work, but it's going to be like trying the same pattern of numbers each time. We're just plugging in different numbers. So because there's only so much space here, I included the one that worked, which is C. I made my Venn diagram. I knew I could plug in A and B first. When you're making your Venn diagram, that's always a good place to start. Now, A and not B is right here, also 0.1, and not A and B is right here. So they gave me kind of my 3 parts of the Venn diagram. And then I tested out my independence rule. So probability of A is 0.2. I knew that because I added everything inside the A bubble. Probability B is 0.5. I added everything inside the B bubble. And then I tested out my independence rule, found out that it worked. So yes, they are independent for C. If you try out that same pattern on the other numbers, it will not work. You will not get 2 things being equal in the end. Okay. In parking lot, 200 cars, 50 plus 30 plus 20 is 100. So we know that 100 of those cars are not green because they're either white, red, or silver. And we said there can only be one color on a car. We don't know of the other 100 if they're all green, if some of them are green and some of them are purple. We don't know. So we can say that at most 100 cars are green. Like if all the ones we don't know about are green, that would be 100. So at most, our probability should be 0.5, 100 out of 200. So when you look at all your possibilities, 0.6 is the only one that's beyond that description of at most 0.5. So that is the one that is not correct, not true. Okay, number 9. So they told us the probability for A, B, and C failing. So I did 1 minus that to find the probabilities of them not failing because we are interested in them not failing. And for the device to work, all 3 of them, of the pieces of it have to work, the 3 components. So if this is really one of those at least one things, like if it's at least one fails, the whole thing fails. So for it to not fail, all 3 have to work. And they said they're independent, which means we can just multiply them. And we get 0.922. Okay. Now 10 was a doozy of a problem. I quite enjoyed doing it as a math teacher. I hope you enjoyed it too. So let's see. They told us probability of A, told us probability of B, and they told us the probability of B given A. So these were given. Now, my goal here was to do a Venn diagram and figure out what all our parts are. I know what A and B are, but I don't know how much of that overlaps inside the Venn diagram. I need more information here. So I used what they gave me. They gave me probability of B given A. So I used my formula for that, plugged in what I knew, and I was able to find probability of B and A. So that's the middle part of my Venn diagram, the football part of my Venn diagram. So then that allowed me to, okay, if I knew the probability of A was 0.55 total, I could go 0.55 minus 0.33 to get 0.22, because I knew those two numbers should add up to 0.55. Same over on the B bubble. If I knew the total, the B bubble should add up to 0.4. I've got 0.33 plus X basically equals 0.4. So 0.4 minus 0.33 gives me 0.07 for the rest of the B bubble. And then now that I knew those three things, I could figure out what my outside number is. I could say, okay, everything should add up to 1. So 1 minus 0.22 minus 0.3 minus 0.07. So minus all the parts gave me 0.38 for my outside. So now we're using, okay, we say probability of at least 1 is the same as 1 minus the probability of none. Let's see, I've already forgotten. Oh, scholarships, right. So this is the key. You see that phrase? That's a clue that you're going to do your 1 minus none trick. So the probability that we're at least one of the two scholarships. Now, keep in mind, we could attach this as probability of A plus probability of B plus probability of A and B and all that stuff, but dealing with overlaps and double counting, it gets complicated. So it's easier just to do, what's the probability of getting none of the scholarships? That's 0.38, we just found that. And then go 1 minus that to get 0.62. So this problem by itself used most of the rules that we learned, and it used the model of a Venn diagram. So keep all those rules handy in a place that they're easy to find on the test. And when stuck, draw a Venn diagram. If you get stuck, draw a Venn diagram. We spent a lot of time with those. We spent time with two-way tables and then tree diagrams as well. I let tree diagrams be more of a focus on the free response. So it's not really going to show up very much in the multiple choice, but that will show up more in the free response. All right, that's it.